Hey everybody, Professor Leach here. Today we're going to look at integrating products of powers of trig functions. Really, this is going back and deciding when can we use substitution? Because the more important question is, when can we not use substitution? That's going to be more interesting to us because we have a method for substitution. We just need to practice that. So we need some kind of alternate method if we're going to have not substitution. So the question that we're trying to answer is, under what conditions on P and Q do we get to use substitution? So the setup was, if we want to make the substitution W equals sine X, we need one factor of cosine X to be the dW. Then if we have extra factors of cosine X, we can convert those to sine, and that's useful because sine is just going to be W. So if we have a cosine squared left over, then we can write that as 1 minus W squared. So we're going to make our substitution. We're going to save what we need to save for the dW, and then we'll convert the rest. That's the big idea. So if we have make the substitution W equals tangent, then dW is secant squared. So this is what we saw yesterday. We have to have two factors of secant to be the dW. Then any leftover secants can be 1 plus tangent. Any leftover secant squareds can be 1 plus tangent squareds. What we want to observe for this to work, for this converting the rest of them to work, they have to convert in pairs. That's the important thing that we want to notice. So note that the convert the rest step requires even powers. Note. We only get to convert. We only get to do the convert the rest on even powers. So convert the rest requires pairs. So if I have a cosine to the fourth, I got to save one, and I'm going to make a substitution sine. If I save one factor of cosine to be the dW, I'm left with three factors of cosine that I can't convert. I only get to convert on even powers. So the idea is, what conditions on P and Q do we get to use substitution? Any questions? So that's the task that we want to sort out. We did an example yesterday where we had, so let's recall this example from yesterday, where we had secant, I think it was to the fourth, and tangent to the fifth, x dx. In this case, we can make the substitution W equals tangent because we have an even number of secants. So it was the even number of secants allows us to use, to substitute W equals tangent. So this substitution works because the dW is secant squared, and there are two secants left over that we can convert. So then I can use the secant squared. X is 1 plus tangent squared x. So in this problem, secant to the fourth, tangent to the fifth, W equals tangent works as a substitution because I have two secants to be the dW and two secants left over that I can convert to tangent. That's what made this work. So this substitution works This substitution works since we have two factors of secants to be the dW We have 2 factors of secant for the dw and 2 left over and an even number left over to convert to tangent. So that's why this worked. This substitution works since we have 2 factors of secant x for the dw and an even number of factors of secant x to convert to tangent x. Our job is going to decide what is it about the 4 and the 5 that allows us to do this. So, as another example, yesterday we saw this example as well. The integral of secant to the 5th x tangent to the 5th x dx. In this case, the tangent substitution doesn't work. In this case, when we write w equals tangent x, I should specify it doesn't work the way that we want. It doesn't work the easy way. And let's see what the thinking is that goes behind that decision. So w equals tangent x, that would require a dw is secant squared x dx. And secant squared x is 1 plus tangent squared x. In this scenario, this substitution is not going to work because I need to save 2 factors of secant for the dw, but then I'll have an odd number of secants left over that I can't convert. We can only get to convert the rest on even powers. That's what makes the substitution go. So what we had up here, we could split the secant squared, secant to the 4th into a secant squared, and to convert a secant squared to be the dw, and then a tangent that we're going to substitute, and that can be raised to the 5th power. However, when we had secant to the 5th, this tangent doesn't work. Doesn't work well. Because when we save 2 factors of secant for the dw, when we save 2 factors of secant x, there's an odd power of secant left over. So what's going on here is we have, if I have a secant squared for the dw, secant squared can be convert to 1 plus tangent squared, but then I have this rogue factor of secant that I can't do anything with. I've got this secant x. I can convert a square of secant x. I need the 2 factors of secant x to be the dw, and then tangent is the substitution that I'm trying to make. So I can take care of the tangent. That's the substitution we're trying to make. Secant squared is going to be the dw. I wrote xw over here. It's supposed to be an x still. The secant squared x to x is going to be a dw. This 2 factors of secant can be converted to 1 plus tangent squared, and that'll be just 1 plus w squared. But I've got this rogue factor of secant for which we don't have an answer. This is the one that we can't convert. So we've noticed something. I'm going to point this one out. We've noticed that if we want to make the substitution w equals tangent x, that's going to work if the power of secant is even. If we have an even power of secant, then we can make the substitution w equals tangent x. So we've made a conclusion. Let's summarize that. So to substitute, so good news, we have a discovery. So this is in the category of integrating secant to the p of x times tangent to the q of x to x. If p is even, then we can make the substitution w equals tangent. If p is even, then we can substitute w equals tangent x. And we should note that the only requirement here is that p is even. Tangent can be whatever it wants. If I have tangent to the fifth, I just had a w to the fifth. If I had tangent to the sixth, that would just be w to the sixth. It wouldn't mess with what's going on with my secants. So let's do an example. If I have an even power of secants, what jumps out at us in this case is that there's an even power of secant. It's a secant to the sixth. And I've gone with tangent to the fourth because it doesn't matter if the tangent is even or odd. So we see an even power of secants. That means w equals tangent is on the table as a possible substitution. This is where we make our decision. Even power of secant x. That says that we can make the substitution w equal tangent x. If we want to make the substitution w equals tangent x, that's going to require two factors of secant to be the dw. And then we'll convert the rest in pairs. What works is that it start off with 6. I save 2 of them to be the dw. The other 4, since it's even, can convert to tangent. Secant squared x is 1 plus tangent squared x. So I get to use all these parts. Here's how it's going to look. Secant to the 6th is going to be split up into secant to the 4th. That'll get converted. Secant to the 4th, x. I need 2 factors of secant to be the dw. The tangents are all going to become w. And it doesn't matter what these are raised to, it's to the 4th, but that was not part of what we needed. And then the dx will combine with the secant squared to be the dw. The important thing here is after we cut off 2 factors of secants to be the dw, there's an even number of secants left, or an even power of secants left that we can convert. Secant to the 4th x is just secant squared x squared. This is good because secant squared is 1 plus tangent. So this is just going to be a 1 plus tangent, which is going to get replaced with W. Oops, and it's being squared. So how we're reading the secant to the 6th, 4 of them is going to be the square of a secant squared. So it's going to be a 1 plus tangent squared. 2 of the secants are going to be the dw, and then the tangents is the substitution that we're making. So our integral really looks like the integral of 1 plus tangent squared squared times a secant x to x, secant squared x dx, and a tangent to the 4th. I started doing the color matching thing, so now I cannot stop. Now we can see how the substitution is going to go. If you're thinking, gosh, this seems like a lot of writing for something that I could just look up on Wolfram Alpha, getting the answer is not the point. And writing all this stuff down is also not going to be the point. But now we can see how this is going to be, this integral in x becomes an integral in w just by substitution. So I have the integral of 1 plus w squared squared times w to the 4th dw. So this 1 plus tangent squared squared becomes 1 plus w squared squared. Secant squared dx is the dw. Tangent to the 4th becomes w to the 4th. That was the original substitution we were trying to make. What made this work is that p is even. We have an even power of secant, so the substitution is w equals tangent x. And now this is not so bad because this is just a polynomial. So now we're just integrating a polynomial. So we're going to have, let's see, 1 plus 2w squared plus w to the 4th. Then I'll multiply everything by w to the 4th. And so we're integrating w to the 4th plus 2w to the 6th plus w to the 8th dw. We integrate in w first. So we'll have a 1/5 w to the 5th plus 2/7 w to the 7th plus 1/9 w to the 9th plus c. I dropped the integral in dw because we have done the integral thing. We have added 1 to the exponent and divided by the new exponent. This is not acceptable as an answer because this is an answer in w and we have to answer in x. So now we just go back and put the tangents back in. So our final answer will be a 1/5 tangent to the 5th x plus 2/7 tangent to the 7th x plus 1/9 tangent to the 9th x plus c. So we've made some progress. We're integrating a product of powers of secants and tangents. If it's an even power of secants, then we'll make the substitution w equals tangent x.
Professor, I have a question.
Yes.
I'm trying to figure out the best way to ask this. So where it says dw equals secant x dx, Well, I guess I've been solving for dx, and then that cancels out that secant squared, and you're
Okay.
left with a dw.
Yes.
Okay, I just want to make
So
sure I didn't miss something.
that will still work. So if you plug in the dx as dw over secant squared, that'll cancel out 2 factors of secant and leave 4 behind. And so you'll be able to convert the secant to the 4th into tangents.
Got it. Okay, thank you.
Any other questions? So, so yeah, that's it. We've solved what we've successfully discovered a substitution that we can make. So if P is even, if the power of secant is even, then the substitution is W equals tangent X. We know that that will work for any power of W. In this case, even if it's negative. So if we have secant to the 6th times the square root of tangent, that will work as well. But right now we're restricting ourselves to integers because we're trying to analyze the problem through substitution, and integers is a better place to start. Any questions? That raises an important question. What if P is not even? Every time we find a solution, we have to examine the case where the solution doesn't work. We have an answer for when P is even, and it looks like the power of tangent doesn't matter. So we're also going to have to look at what happens when P is odd. Then we're going to have to look at whether whether the power of tangent matters at all. So one thing to note here is that the only requirement here was that P is even. The only requirement here is that P is even. This it would work if the power of tangent is a fraction. If this was tangent to the 1/2, that would be no problem because that just shows up down in here. It would even work if we don't have tangent at all, which is the weird case. The only requirement is even. So if we wanted to integrate, for example, just secant to the 6th x dx, this is the weird one. It's a power of secants and tangents. And the substitution that we're going to make is tangent. We have an even power of secant. There's an even power of secant, so the call is that W is tangent X. The reason that this is the weird one is that my original integral does not have any tangent in it yet. dw is tangent X, so the dw is secant squared X, the X. And then any even powers of secants, that's where our tangents will show up. That's where we're going to get our tangents. So even power of secants says W equals tangent X, regardless of the power of tangent, even if the power of tangent is 0. So the read on this integral is there's going to be a secant to the 4th X. I'm going to save the secant squareds to be the dw. And I'm going to do the same thing to the secant to the 4th that I did in the previous problem when I had all those extra tangents. What makes this weird is that we have to make a substitution for stuff that isn't even there. But they do show up once we get to the convert the rest part. So the secant to the 4th or sorry, the secant to the sixth integral in x is going to be an integral of 1 plus w squared squared dw. The remainder is left up to the reader. Side note, I'm the only one that gets to stop a problem with a dot, dot, dot. You can't be like, oh, taking a test or something and put like, oh, well, then there's some other stuff. Because your job is to find that other stuff. Any questions? The way that we're going to ask these problems, there's not a whole section of, I treat this like it's its own section. It's like it's like DVD bonus material for the section on integration by substitution. So these are like the deleted scenes from the DVD version of the book, where we take a deeper dive into integrating products of powers of trig functions via substitution. Because what we want to do is, there's actually a larger point to why we would want to study products of powers of trig functions. And it comes from a step further in your substitution journey called trigonometric substitution. So we want to look, what happens in a trigonometric substitution is that we make a substitution that's really weird, a trigonometric one, and we end up with an integral that will be a product of powers of trig functions. And we have to know how to integrate that. If we do the trigonometric substitution and end up with one of these scenarios, that means we need to stop and go back and look for the substitution that we could have made at the beginning. So it's important to be able to identify these things so we don't just blindly follow some process. Because that leads to things like PEMDAS, and that leads to things like sometimes 1/3x means 1 divided by the product of 3 and x, and sometimes it just means 1/3 of x. And those kind of rules are trash. We can't be separating things out into all these little different categories. So we've got to build one system and then see how that applies to many scenarios. Any questions? This is my objection to football. Football is dumb because its rule set is terrible. And they have to have the slow-mo, and they have to come up with the reasons for the slow-mo. And the argument is, well, we have to make sure that the refs are getting the call correctly. But you can only, you have a limited number of challenges that you can make. So are you really concerned that the refs are getting the call correct? Or are you just crying that it didn't go your way? I think it's the latter, because otherwise, if we really cared about the truth in football, as if there is something like that, then if you think the call is wrong, you would just challenge. You would be allowed to challenge. But because it's like, oh, well, you can challenge, but only up to a certain point. And it's because, and we like to think it's like, oh, it's because we're sportsmen. But our first instinct is to recognize that if you were given unlimited challenges, then all the other team would do, all you would do is challenge every call that didn't go your way. So we already know that even though we're all sportsmen here and we'll do sportsmanlike conduct, we know that we won't. We know that if you're allowed unlimited challenges, that it would just ruin everything, because people would just challenge. We know that our answer is that we would be unsportsmanlike, no matter how much we say we care about sportsmanship. We know it's a lie. Do you know what I mean? So it's my problem with football. They have the dumb set of rules. And that dumb set of rules, because we say, oh, we care about integrity. Oh, we don't want our players on steroids. It's not that we don't want our players on steroids. We absolutely want our players on steroids. That is what the audience wants. We just don't want to hear about it. We just don't want it shown that we're like, oh, the way to get into football is to steroid yourself out. Because there's a lot of people in football that are like 6.5 feet tall, well over 300 pounds, and still athletic. Oh yeah, I'm sure that's just naturally occurring. And if you separated out a league for steroids versus no steroids, I can tell you which one people would watch. They would watch the interesting one where everyone's athletic and huge. And we would do the same thing. We would say, oh, we care about our players and their health. It's like, oh, no, you don't. You have a whole sport that has a suicide problem and a brain damage problem, and you're still just trying to make money off of it. So no, you don't care about the players. You care about making money. Anyway, my favorite example of this is like, well, at least in the United States, no one cares anymore about the Tour de France. No one cares anymore. Because our steroid guy got outed for being on steroids, even though he was like, oh, dude, everybody up here is on steroids. And then he turned around, it's like, oh, right, guys? And then all the other guys that were on steroids, like, oh, no, not me. You know what I mean? So anyway, I also don't understand the obsession with college football. Why would I want to watch a bad version of football? Why would I want to watch people play the game who are just objectively worse at it? You can tell they're objectively worse at it in college because in college you can get away with things like trick plays. Oh, look, we did a sneaky play. The fact that the sneaky play works means that your players aren't very good. That's why it's funny when the hidden ball trick works on Barry Bonds. Because the hidden ball trick has to stop working in high school. And if you try it in my baseball game, if you try the hidden ball trick in the major leagues, I'm like, oh, we're trying to put on a show. $10,000 fine for the team, not the players. You know what I mean? And if I find out that the owner passed the fine on to the player, then I triple the fine for the owner. And if he does it again, I take his team away and sell it to someone else. And he doesn't get compensated because I don't really care about these millionaires who want their gladiators to fight in the arena. You know what I mean? I guess my overall point is, if I can sum it up into one system like I try to do with math, don't lie to us by saying that you care about sportsmanship. You care about money. At least be honest with us. But then again, what do I know? I haven't watched baseball I stopped watching baseball in 2009 because I didn't watch baseball in 2010 for outside reasons, not for any these kinds of reasons. I stopped watching baseball in 2010. So you can guess, and I haven't watched baseball since, so you can guess what team I am a fan of. Because it's baseball, and baseball fans are really superstitious. It's like, oh man, I didn't watch in 2010. And then my team won the World Series. Well, I can't watch now. I ignore that it didn't happen in 2011, but 2012 confirms my suspicions. Like, see, I didn't watch in 2012, another World Series win. Then people are like, oh, well, what about 2011? Michael, quiet, you. We're feeding into superstition here. 2013 also gets ignored, but 2014, see, it's true. Anyway, so All that is beside the point. We've made an important discovery in the category of secant to the P, tangent to the Q. If P is even, the substitution call is W equals tangent X. That's the way, what we're going to do. Even if we don't see any tangents there at all. Even power secant, W equals tangent X. We have solved that one. Your job, what if P is odd? So that's going to be your first assignment. If P is odd, what's the substitution? What if P is odd? Is there anything else that we need to make the substitution go? This is the first, this is what you want to examine. What if P is odd? What's our substitution call? If P is odd, we know it's not W equals tangent. So what do we need? So I guess really my question is, what do we need to make W equals secant X the call? So let me just rephrase that. What do we mean? What do we need to make W equals secant X work? We got to save for the DW. What do we need to save for the DW? And we need an even power of tangents to convert to secants. So we'll talk about that one tomorrow. That'll do it for today. I'll see y'all on tomorrow. Thanks for playing and peace out.